I'm Will. I'm with MediaMath, and I'm going to talk about clustering in Go. So just as a heads up, I'm going to do a little bit of like live demo stuff, which is probably going to catastrophically fail. And if that does, we can all just laugh at me. I'm totally cool with that. So a little bit about myself. Actually, real quick, who here uses Go in some way? I know you do. All right, handful. Anyone written any Go for fun that didn't raise their hand? Okay, so some light amount of experience. Did anyone actually come to GoTo last year in the crowd? Well, I know you guys did. That's not fair. Okay, did anybody actually come see my talk last year on Go? This is not the same talk, so don't worry. I'm not like shilling the same stuff. Anyway, a little bit of a Go enthusiast. I actually, sadly, don't write a lot of code anymore myself, which is just what it is, I guess, sometimes in life and career, whatever. I lead up the infrastructure and platform teams at MediaMath, and I'd be remiss not to say that we're hiring, because we're hiring. So if you're interested in those sorts of things, come talk to me later. Okay, so really quickly, why Go? This is not a Go pitch. I'm not going to actually pitch you on using Go. In fact, I think I'm going to say some things that might make you think that Go is not good, which is totally not true. Go is awesome. But like the really quick basic things, which I'm glad that none of you came to my talk last year, because this is literally the same slide, almost. It's easy to build services. Like it's just really quick to build microservices, since that's the buzzword. It's got a great standard library. If you want to build something like truly from scratch, you have pretty much everything that you need to do that out of the language. And if you don't want to build something from complete scratch, there's a ton of, and a very quickly growing community that has a ton of libraries and a ton of utilities, a couple of which we'll talk about soon. But topic du jour, if you like Docker, that thing's in Go, and there's like a lot of other awesome examples out there. The built-in tooling is also amazing. In fact, I think this is one of the places where Go actually really excels over other languages, and tools like GoFumped. So the built-in formatting stuff that exists within Go that makes it possible for you never to have an argument about whether or not the brace goes on the next line, or whether or not there's a space between the function name and the open parens. Like, I'm really happy that I never have to have the argument ever again. Go Test, which is a package that basically has baked-in tests and make it really easy to build your own, whether it's unit tests or functional tests or whatever. Go Vet, which basically says, hey, this code looks suspicious. You should make it better. That's not really a good description. You should go look it up if you're interested in Go. And then like the race condition checker, which has been quite handy at times for me. Something you'll see a couple times in the demos that I'm going to hopefully make work in a second are the compile times. They're like really fast. It's really like more of a scripting language when it comes to just being able to do Control C, up, arrow, enter, and test real quick. So that's super spoiling. And it just feels productive. I can't quantify that in any meaningful way, but I like it because the code that I wrote to put this thing together, I don't think it took me more than like 6 hours. Anyway, cool. So why talk about clustering in Go? Well, clustering is not really batteries included in Go. And when I say batteries include, I mean like there are a lot of other languages that have things that are really closely tied to language or closely affiliated with the language that are like the preferred mechanism for clustering. So things like, Akka cluster, Erlang OTP, like Quasar, I guess, like stuff like that. Like Go doesn't really have a de facto that I'm aware of. And there are a lot of newer libraries, but none of them are really that mature from what I've seen. So like, I think Beehive and Go Circuit are a couple that come to mind. And so more often than not, services that are out there kind of roll it themselves. And I think a decent example of rolling it yourself and then having to roll it again a couple times as you understand your problem space better has been like InfluxDB, which has had to actually go through and rebuild a bunch of their clustering a few times over for good reasons. So what I'm going to walk you guys through is like one way of building a clustered stateful service. There are many ways to do that. This is not the perfect way. This is just a way. I only have so much time to actually like demonstrate a couple different tools. So you're going to get to see those tools in action. And yeah, cool. So let me just set up a fake scenario for the thing that we're building. Let's say you're a business that has like multiple data centers. Each of those data centers is like distributed in different parts of the world. So hypothetically, like Chicago, Hong Kong, Amsterdam. I picked those three in particular because there's like anywhere between 180 to 160 milliseconds of latency between each of them, which means these events happen. When they happen concurrently, it's non-trivial to tell the other data center that they happen, and certainly you can't do so in a way that says, wait, you can't do anything else until I tell you. And so what we want to do is we want to build a service that counts those events. This is actually not too dissimilar from what we've got at MediaMath. We have several thousand servers. We have millions of events per second. We have 9 data centers. We have tons of concurrency, tons of different types of events, and it's really important for us to be able to handle those events with a specific bounded latency budget. And if we miss that budget, we effectively are missing out on potential money. So the constraints that we have here is that counting should be fast, right? We can't actually afford to cross the ocean every time. We can't afford to wait on that transfer back and forth every time an event happens. Certainly couldn't do that synchronously. And count should be correct. So we should try to make it possible not to lose events, right, as they are effectively incremented upon. So for those of you guys who are familiar with the CAP theorems, it's starting to look a little bit of like an AP system, right? Basically, I need my operations to occur and be available often in the state of a potential partition. Cool. So let's get started. Just as our bedrock, I'm going to do a really basic counter service. So we'll start with one node and a atomic integer. Nothing fancy, right? So those two little curl lines, and I did write the code. We'll demonstrate it in a second, but that's basically what you're going to expect, right? It's if before I do the increment, if I do a get on it, I get 0. After, I get 1. Yay, cool. So this is the code. It's pretty much exactly what I just said. There's a counter with an integer. If I run an increment on it, it increments the counter. If I count, then it tells me what the counter's value is. Cool. So I'm going to do this in my browser and hope that it doesn't break. Cool. I'm incrementing it by 1. And incremented counter to 1. Wow, this is working so well. Okay, it's incrementing me 3, 4, 5. Yeah. Okay, close that. Awesome. All right, well, that was really nice. That worked. It's always good to get a running start with the demos that might totally crash and burn. Oh, Microsoft error reporting. Like Excel, crashing and burning. So that's cool. We have one node and one data center. Not particularly useful, have definitely not met the needs of the hypothetical situation that I brought up, which is lots of data centers, lots of events happening distributed. So next step is to CoDistribute said service. So we're going to take that same exact thing that we just built. We're going to put it in several data centers, and then we're going to route those increment requests to the closest node. And so let's do that real quick. Let's see. All right. I'm sure some of you guys in the back can't actually see what's going on. Go run. By the way, every time I do this, I'm compiling. So that was pretty fast, right? Oop. All right, go run, go port equals 4002. Go run, go port equals 4003. All right, so I've got three nodes, and now I'm gonna increment them. Awesome, it still works. This is the best day ever. Cool, so I just did 7 increment requests on that first node. Oh, you can't see it, can you? Damn it. Hold on, let's fix this. Magic. Oh, what is this? That's Excel? Guys, I love Excel. Okay, so here's my second node. Oh no. See, I got to like 12 here, but now when I hit refresh on this one, it's only 2. That's not right. All right, only got to 5. Well, they're counting. They are counting. That's pretty cool. By the way, if I were like actually a truthful person, I would put each of these in different parts of the world, but because I'm on conference Wi-Fi, we're just going to do it on my laptop and pretend. So let's go with that. All right. So I just did a bunch of increment requests. Let's make these go away. Bunch of increment requests. They're different on every node, and it's really obvious because we're not replicating state. All I did was take that counter and like deploy it 3 times. So, Will, you're boring us, I know. So basically, in order to actually get this whole thing to work, we need the counters to talk to each other, which means we need the nodes to actually know about each other, which means that we need to solve for cluster membership. So I think I mentioned at the very beginning that this is a stateful service, right? This is, when I say stateful, I mean like if you were implementing a database, you would carry the state locally. One option would be obviously to like take something like a Cassandra and let it do all the work for you. That's cheating. You wouldn't be here if all I said was using Cassandra with Go, and then like 5 minutes later, it's done. Hooray, bye. So what we're going to do is we're going to use memberlist, and memberlist is a Go library that's built by HashiCorp, which, or I guess managed overseas, yeah, built, sure, by HashiCorp, which is an amazing company that does really good work. They built Vagrant and Console and Atlas and Terraform and all sorts of really great DevOps, Magic, Sprinkly Dust tools. Basically what it does is it manages cluster membership. It's based on SWIM, which is a gossip-style membership protocol. I'll speak a little bit more about that in a second. It has baked-in member failure detection, which is really important, right? Because if you're managing a list of members, you want to make sure that you have an accurate list of who you should be talking to. And this library is actually in use by like Console, Docker, libnetwork, many more. Actually, if you want some fun, like go to GitHub and do the whole code search thing, type in HashiCorp/memberlist, and there's like, I don't know, 40 pages of results of people actually implementing it. So SWIM is scalable, weekly, consistent, in-function style, process, group, membership protocol. That is way more than 4 letters. It basically has 2 goals, which is to maintain a local membership list of non-faulty processes, local to the node, and then detect and eventually notify others of process failures. And so mechanically, the way that works is it's gossip-based, and basically that means it's typically these interactions happen node to node, like one node to another node. And so when a node joins a cluster, it does a full state sync with an existing member. And it begins gossiping its existence to all of the other members in the cluster. Gossip about that internal memberless state actually happens on a regular interval and against a number of randomly selected members. So basically what this means is on like every 3 seconds, every 5 seconds or so, I'm going to gossip to like another 3 people. Hey, I'm here, here's my state. There's also this thing called probes, and probes are basically, hey, are you here? and the expectation there is for you to say, yep, I'm here, I'm alive. And so if a node doesn't act a probe message, it's marked as suspicious. And because of gossip, whenever you mark a node as suspicious, you actually tell the rest of the cluster. Well, sorry, you gossip to the rest of the cluster, hey, this node's suspicious. And then if a suspicious node doesn't dispute suspicion after a certain timeout, it's marked as dead, which is also gossiped out. So you end up getting this kind of cool, eventually consistent, like weakly consistent set of members that's managed across the entire node. So the entire node eventually knows that a particular set of members exist. And every so often, a full state sync actually happens between like two different random members. And depending on how big your cluster gets, like this is really okay and fine in my hypothetical cluster of 3 that's running on my laptop. But if your cluster is tens of thousands of servers, you can't really afford to do this all the time unless you have infinite bandwidth, which is not a thing. The speed of light is like way too slow for that. And so the trade-offs between the bandwidth and convergence time here are configurable, right? You can say I want more bandwidth to be used by this process, and convergence time across the cluster will be less, or vice versa. Cool. So your nodes becoming cluster aware using member list is actually relatively straightforward. This is the code snippet behind it. You basically set a config and then create the member list instance and then join another member list node if there are others. That's pretty much it. At that point, then the cluster does things on its own. So let me show you the whole does things on its own part. We're done with that last example. Member list. All right. Cool. All right, so what I'm doing right now is I'm spinning up. This is the first node. This is the seed node. So I've got a node here who is basically the first node in a particular cluster. I'm going to spin up a second node here in the middle, and I'm going to actually make this a little bit bigger and try to explain it, what's happening. So here we have, I don't know if you can see this. Cool. So what happened was the member joined, and now we have some syncing happening. So that full state sync that I talked about a second ago is actually called a push-pull sync. So let me show you really quickly. This is what the cluster looks like right now. I have 2 nodes in it. I have this node, which was, well, the second node, because maps aren't ordered in Go, or lists aren't ordered in Go, slices I should say. And then here we've got the first node. Okay, cool. So I'm going to spin up a second one, a third one. Member list. All right. And we've got 3. That was pretty quick. That's because of the gossip mechanism. So let me actually go back and take this one out. I just killed it. So if you watch over here, it's going to say suspect. So suspect has failed, no acts received. Suspect has failed, no acts received. It's going to continue to do that until this point where it says marking that node as failed, because the timeout on it being suspect has actually been reached. So if we go back here and hit refresh, now there's back to 2 nodes. Relatively straightforward. Again, I can configure the settings that this entire handshake process will happen, or gossip process, I should say, will happen on a regular basis, and I can either make it converge slower or faster. In this case, because we're doing a live demonstration, I've actually cranked up the time so that I can show you things as they're happening. Yeah, cool, awesome. So I have this counter. They're still disconnected. What are we still doing here? Why haven't you solved the problem, Will? Okay, fine. So I still need these counters to actually, interact with each other in some way. So the way that I'm going to solve for this problem, and again, we mentioned at the very beginning, this is an AP-like system. I'm going to use CRTTs. Mainly because I think CRTTs are super awesome and super cool and like the best invention ever. And I will say really quickly, I'm going to attempt to explain it. I actually have some drawings that are going to attempt to explain it. I would really recommend, if you're into distributed systems, or actually even if you're not, read or watch Scott Meiklejohn's content on this, especially about LASP. He talks a lot about CRTTs because they are actually pretty cool. So what CRTT stands for is it's a conflict-free replicated data type. These are data types that are typically like things like counters, sets, maps, flags, registers. The operations within those types have to be associative, commutative, and idempotent. And because like those are principles of, I believe it's called implemented through semi-lattice algebra, you basically get this thing where you can idempotently, like you can basically merge all the time, right? So the side effect of that is there is no order, or there is, it's technically partially ordered, right? But the data types here do not actually have or support a semblance of order. And because of that, in almost maybe every failure scenario, all you have to do to get these counters to merge again is just to merge again. Like that's literally it. If you have two nodes that can't communicate and then finally they can, just have them merge again. If a node dies and comes back and is out of sync, just have them merge again. Like there's literally every scenario that you have. If you have like several divergent states, just have them merge, and then it will come to consistent convergent state, or rather convergent state. So CRTTs, because of that, again, they're by nature eventually consistent. There is no single source of truth. This works really well for our made-up scenario. So yeah. The most basic of these, the one that I'm actually going to implement, is called a G counter. It is very cleverly named that way because it is a grow-only counter. And it's a counter that has literally just two operations, increment and merge, right? So it only goes up, it never comes down. If you actually want one that can come down too, that's called a PN counter. It's implemented by actually taking two of these counters. One goes up, one goes down, sum them together, problem solved. So the way that G counters work is each node manages its own count. The nodes then communicate their own counter state with other nodes. And then when they merge, they take the max count for each node's value. So the value itself of the G counter is the sum of all the node counts. So let me just give you an example here. We have three actors, Alice, Bob, and Claire. Alice does an increment of 1, Bob does an increment of 1, and then Claire at some point does an increment of 6. So Bob sends its state to Claire, and so Claire here at this point has knowledge of Bob's state before this increment of 3, and knowledge of Claire's own state because Claire, did set action. And so at this point, Claire knows that this happened and counts both of those things, right? So in her storage, she knows both Bob and Claire and can sum them together to 7. Next step, we have another sync here that happens. So we have Bob actually sharing state over to Alice. And so now Alice knows that Bob is at 4, right? Because 1 plus 3 is 4, awesome. And Alice herself has done this increment of 1, and you've got this, that is not 4, that is 5, yes, fantastic. These counters are definitely divergent. Okay, cool. So now we have like this other jump here, and I hope that this math is right. It seems to be. That's pretty cool. Let's just pretend that didn't happen. Okay, so Alice is now going to send her state, which she understands the system to be what she knows and what Bob knows, or rather what Bob has told her up until this point. So she's going to send all of that down to Claire. And since Claire has understanding of Bob and obviously is the canonical owner of Claire's own data, you have Claire now understanding Alice is 1, Bob's 4, right? Because at this point, 4 is bigger than 1, right? So we should take that value because Bob is the canonical owner of said value. And then Claire. So I did the math again in my head. 1 plus 4 plus 6 does equal 11, so that number there is correct. That's basically a G counter. Here's a really, to since drawings are actually not sufficient and we need code, this is basically the implementation of it. So the increment here says, I have my ident, which is the identifier which represents me. And then for every increment, I'm only going to increment the number that I own. To get the count, I'm going to sum all of the numbers that I know. And to do the merge, I'm going to take the largest of any given value that isn't me. Cool. So let me show you this in practice. All right, cool. So just did an increment on the first node. That number is increasing. And oh, that's too big. Now we have, this is actually a raw view of the data structure underneath. So as I increment this guy, this is my node name, this I here. I'm really unique, and so I like UUIDs for node names because they have a ton of uniqueness to them. And then the 7 is the value that I have for my counter. If I do the same operation here on the second node, you will be not surprised at all to notice that they aren't syncing, but now I have a second ident with that UUID of that second node, and that is here the value that matches, right? So if I go over here, this is a totally different set of data. Same thing if I run it on the third node. Does this make sense? This is starting to make sense, come together? Awesome. Well, we still have a problem, which is we haven't merged state yet, so we should probably merge the state. And that's what we're going to do now. So memberless has this thing, which I mentioned before, which is that kind of complete state exchange with another random member. That's called the push-pull sync. In the code, it actually also provides developers a way to piggyback off of it. And because this happens over TCP, you have basically anything that you can send over the wire. You can choose how to serialize it over the wire and how you want to deserialize it on the other side. So there's a delegate. It has basically 2 functions that are important and relevant to this point. It's local state and merge remote state. Local state, which basically kind of dumps the state of someone who's being asked to provide state, and merge remote state does the opposite. It takes that remote state and then merges it in. And that, again, that interval of that full state transfer is configurable. And so we're going to use it to eventually merge the state in the background. So this is what the code looks like. It's exactly what I just said. I'm going to marshal that the state of that CRDT to JSON, and then on the other side, I'm going to instantiate a CRDT for that external CRDT JSON that was just sent over the wire, and then I'm going to merge it into my CRDT. So let's do that real quick. And this is the demo you've all been waiting for. Cool. All right. All right, so as you can see, I mentioned there's a state transfer that happens here. So this is sharing a remote state for push-pull sync and merging it. There's not really any state at this point. If you just go in and look at the contents, it's empty, right? There's nothing to talk about. However, if I go in here and increment on node 2, you see this 1. That 1 is eventually going to show up here. Eventually. There it is. Landed, right? And it's already here because that's where we did it. It's also already here because the sync happened, right? So I'm going to just kind of keep doing this a little bit. I just did it on the third node. We should get in some 5 to 10 seconds. I think I set, yeah, there it is. See that event showing up? Just kind of keep doing this a little bit. So it's here. Not quite here yet. Oh, that happened quick. I must have caught it in between. Oh, there it is. Do you guys catch that? Should I do that again? No? Everyone's tired. It's like the second to last talk on the last day. Cool. This is like, I mean, it's pretty cool to me. It's pretty cool that like, this state transfer happens, a merge happens, the CRTT, again, if the state transfer fails, all that you have to do is do it again. Like just do it again, and then it's gonna happen. So let me actually play with this a little bit. I'm actually gonna kill the second node, and see, it's dead. You actually can't get to it. If I go over here to the first node, well, it's still there, right? The data from the second node is actually still there. And I promise you, sorry, not that node. Let's do, just to prove to you that the cluster's gone, the second node's gone. The second node's gone. We only have 2 nodes here, but the data from the second node is still there. So if I spin it back up, it will rejoin the cluster. I'm going to increment on it, and eventually, there it is. You see a fourth, right? So because I assigned that new unique that new unique UID, I now have a 4th item here. So the nifty part here is that the amount of state that you can potentially lose is basically a function of how recently did the last state transfer happen, right? And so in cases where you desire a lot of correctness, you can tune the amount of correctness there based on how often you'd like to do some sort of a state transfer. Obviously, there are actually a lot of interesting things that you can do on this point to ensure that state transfer happens locally as opposed to remotely. If you have multiple different data centers, and state transfer can happen between nodes in the same data center, which is cheaper than going over the network. Those sorts of things are possible, but I'm not going to go through them here. So awesome, we have achieved success. It's very eventual, right? It took us about 10 seconds for that first sync to happen, but we did sync. Memberless did solve that problem for us. There are obviously ways that you can sync faster. One way to sync faster, which actually would be very stupid for our use case that we're talking about right now, is to broadcast on every increment request. I say very stupid because we just said that we want increments to be fast, and we want bandwidth to be, the amount of bandwidth used for this entire operation to be low. So if I broadcast on every single increment request, I'm blowing through that entire requirement. But let me just go ahead and do that so that you can see how this works. So I have this broadcast state function here, which appends a broadcast event into the queue. And then on the other side, anyone who receives a broadcast event gets this notify message function invoked. And then they can do the same thing that we did previously, which is instantiate the CRTT, merge it in, and then get the merge value. So quick demo. I have this line of code. It's a Go routine which broadcasts the state. Let's hope this works. Again, it's compiling super quick. Promise, this is not a Go talk. All right, cool. So I'm going to hit increment several times, and you should see here several of these receive broadcast to remote states. Actually, if I spam this a ton of times, you'll see lots of those. You see lots of those on a few of the different nodes. So again, this is just a somewhat clever way of ensuring that the cluster converges sooner rather than later. But again, it's not necessarily a suggested mechanism. Cool. So what I would do next if I was actually building this thing as a service is I would build tests. My source code, while up on the internet and available for all of you guys to critique directly and make fun of me on Twitter for, doesn't have any tests. So because I said that, it's okay. So you can't shame me, although I will take complete blame for being a bad developer. After tests for that thing, I would probably implement some form of persistence and time windowing. One counter that just goes up forever is probably not that useful. So, I would also implement more than one node per data center. Again, this is just my laptop, so it's a very small and cheap data center. But we would, if we actually cared about it being an AP system and being available, we would put lots of these things in every local data center and allow them to sync. I would also run and implement Jepsen testing for this, or some other form of correctness validation, right? So modeling it with TLA plus or similar. Would probably also implement a real RPC layer, right? So memberless delegate is pretty useful, but if I wanted finer performance control or authentication authorization control, so not just any node can join my cluster, I would want to implement my own RPC layer there. And then as just kind of part of the last set of extremely important to-dos, I would run it as a unikernel within Docker running inside a VM in AWS. And then I would sprinkle DevOps magic dust on it, and then I would have achieved peak microservice, which is what we're all here to do. So, yeah. There's one takeaway. It's actually not that hard to build clustered services in Go. Again, memberless is your friend. CRTTs are also your friend. All of this code is up on GitHub. You can play around with it, and again, nitpick as you will, ask questions, whatever. And that's it for me. So if you guys have any questions. Say it one more time.
How do you handle fault tolerance to the clustered or distributed architecture?
Okay. The question was, how do you handle fault tolerance in a clustered or distributed architecture? There are many ways to do that, and there are, I guess, several different definitions of fault tolerance that I would be able to take here. But in this case, I'm piggybacking completely off of the fault tolerance, or rather failure handling that memberless has, and because it is a very weakly consistent system, those are the constraints that I have. If I wanted to try to enforce, stronger handles, I could do other things, like maybe try to implement some sort of a dynamo model where I actually have more control over the amount of ways that a piece of data is actually sent around. I don't know if the answer to this question. Any other questions about Go or memberless or CRTT or? So state, I guess the question was, how do you reduce replication for the amount of state that you're actually, as the amount of data? So are you specifically talking about the CRTT implementation or the memberless implementation? Like the data that we care about replicating is the counter, but memberless makes that possible by sharing the cluster state. So which one are you asking about?
So I guess memberless only does like full replication, basically.
Memberless primary concern is the actual member list. We happen to be piggybacking off of the memberless protocols to facilitate transport of the state in the CRTT. So there are a lot of other ways that you could do that, right? I think actually when I originally wrote this talk, I was going to do it first in memberless and then build my own RPC layer that did something that was more akin to a dynamo, where I could say, do a quorum write where it funnels out to quorum waits and then does some sort of like a 2 or 3 phase commit to ensure that all the writes are made. But I didn't have time for that. The problem, I think, with what you're saying here is that my assumption is that every node has the state of every other node in the CRTT in eventuality, and that is correct because we're using memberless to do that work. So another way to do that would actually be to build like some sort of a ring or partitioning or sharding, whatever word you want to use, to structure the movement of the data and the limitation of the data to only relevant sets of nodes. So one of our systems at MediaMath actually makes huge amount of this. It borrows heavily from the vnode concept that Cassandra has, where basically you have pools of data that are classed within like a mod ring, and that data is effectively sharded and pinned to a specific node, and the cluster sizes don't have to be the same across all the data centers. They're effectively like a piece of data is replicated to a particular node in a cluster on the other data center. None of that's implemented here, sorry. Cool. Thanks, guys. Appreciate it.